Welcome to this explainer. Today, we're going to treat geometry exactly like a detective story, using basic clues to crack the most complex exam problems out there. Whether you're just looking to solidify your foundations or you really want that extra edge to speed up your problem solving, you are definitely in the right place. We're going to build a completely interconnected logical toolkit that takes the guesswork entirely out of geometry.
Okay, so here's our roadmap for today. We've got 5 stops: going back to angle basics, navigating parallel lines, cracking the triangle code, unlocking polygon secrets, and finally, how to avoid those super common exam traps. Let's kick things right off with Section 1, back to angle basics. You probably already know the usual suspects here, right? We've got acute angles sneaking in under 90, perfect 90-degree right angles, obtuse angles stretching up to 180, and reflex angles bending backwards between 180 and 360. Getting these specific profiles down cold is absolutely crucial because it means you can just eyeball the problem and instantly know if your calculated answer actually makes sense.
And here is our very first magic number, 180 degrees. Angles on a straight line are always going to add up to exactly 180. Just picture a perfectly flat horizon. If you've got 2 angles sitting there on that line and one is, say, 65 degrees, you instantly know the other one has to be 115 degrees. It's just a non-negotiable rule of the geometric universe.
Now, what happens when you do a full turn? Well, angles entirely around a single central point will always sum up to our next magic number, which is 360 degrees. So if you're piecing together a circle of angles around a point, and you have, let's say, 120 degrees and 80 degrees, well, that adds up to 200, right? You immediately know that the missing piece of the puzzle, your x, has to be 160 degrees to complete that full 360-degree rotation.
Okay, what about vertically opposite angles? If you have 2 straight lines crossing paths, they make an X shape. The angles directly across from each other are totally identical. They mirror each other perfectly. If you figure out one angle is 72 degrees, you don't even need to do any math. The angle directly across from it is automatically 72 degrees as well.
Moving right along to Section 2, let's see what happens when we navigate parallel lines. Meet our primary suspect for this section, the transversal. Basically, it's a line crossing 2 parallel lines. Imagine 2 perfectly straight train tracks running side by side. The transversal is the road that cuts right across both of them. And when that intersection happens, it creates this really fascinating, totally predictable network of angles.
Now, check out the difference between corresponding angles and alternate interior angles. Corresponding angles sit in the exact same relative spot at each intersection. So, if the top right angle up top is 58 degrees, the top right angle down below is also 58 degrees. Alternate interior angles, on the other hand, they play a little game of ping pong inside the parallel lines. They're on opposite sides of the transversal, but they're still perfectly equal.
And if we zoom out completely outside the parallel tracks on opposite sides of the transversal, we find our alternate exterior angles. Guess what? They're perfectly equal too. It's the exact same logic as the interior ones, just pushed out to the absolute edges. Spot one and you automatically know the other. But hey, don't forget the co-interior or same-side angles. These guys are trapped on the same side inside the parallel lines. Now they aren't equal, but they add up to our first magic number, 180 degrees. So if one inside angle is 75 degrees, its neighbor right below it on the same side just has to be 105 degrees. They team up to hit that 180 mark.
All right, Section 3, cracking the triangle code. Let's take these street rules into a closed room.
First rule of triangles, no matter how you stretch or squash them, the interior angles will always total exactly 180 degrees. Seriously, it doesn't matter if it's a super tall, skinny, acute triangle or a wide, flat, obtuse one. If you know 2 angles are, say, 70 and 55 degrees, that's 125 total. Your missing third angle is completely locked in at 55 degrees to hit that 180 target. Now this exterior angle theorem, this is an absolute game changer. If you extend one side of a triangle outward, that new outside angle is exactly the sum of the 2 interior angles further away from it. It's a fantastic shortcut. So if your 2 opposite inside angles are 40 and 65, don't even bother calculating the third inside angle. Just add 40 and 65, and boom, your outside exterior angle is exactly 105 degrees.
Moving on to Section 4, unlocking polygon secrets. Let's scale this up to bigger shapes.
Using the formula n minus 2 times 180, we can see this perfect mathematical rhythm. You literally just add 180 degrees for every single new side you discover. A 3-sided triangle is 180. A 4-sided quadrilateral is 360. Pentagon, 540. By the time you get to an 8-sided octagon, those interior angles add up to a massive 1080 degrees. This formula basically maps the internal space of any polygon out there.
Let's zero in on regular polygons for a second. When you hear the word regular in geometry, I want you to think of perfect harmony. It means every single side length is identical, and crucially for us as detectives, every single interior angle is the exact same measurement.
Let's actually walk through finding a regular hexagon's interior angle step by step. Okay, first, you know it has 6 sides. Using our formula, 6 minus 2 times 180, you get 720 degrees total. Because it's regular, you just take that 720 and slice it evenly into 6 pieces. The result, every single inside angle of a regular hexagon is exactly 120 degrees.
But here's where it gets really wild. No matter how many sides a polygon has, if you add up one exterior angle at each vertex, it will always stubbornly hold to our second magic number, 360 degrees. Triangle, octagon, or a giant 100-sided polygon, it doesn't matter. If you walk the perimeter and add up the turns at every corner, you always return to a 360-degree fold turn. For a regular octagon with 8 sides, just divide 360 by 8, and you know each outside angle is exactly 45 degrees.
And the master link connecting the inside and outside of any shape? It's the straight line they form at the corner, which brings us right back to 180 degrees. If the interior angle is 135 degrees, its exterior partner sitting on that same straight line simply has to be 45 degrees to complete the 180.
Finally, Section 5. Let's talk about avoiding common exam traps so you don't lose silly points.
Look, these are the classic traps where people trip up. Mixing up corresponding and alternate angles is a huge one. Forgetting that co-interior angles sum to 180 instead of being equal. Trying to use the regular polygon division shortcut on wonky irregular shapes. And of course, forgetting that ultimate stabilizing rule. Exterior angles always sum to 360 degrees no matter what.
So here's your absolute ultimate checklist to lock in those points. First, actually draw clear angle markings on the page before you try to solve anything. Write down the specific angle rule you're using right there next to your calculation. Always include the degree symbol, and just take a second to double-check those triangle and exterior totals. Make the invisible visible for the examiner.
We've completely cracked the code on abstract shapes today, but think about this. Where else do these hidden, mathematically perfect angles shape the architecture of our physical world? Once you hold this geometric master key, you're going to start spotting these clues everywhere. From parallel transversals and bridges to regular hexagons perfectly tiled in a beehive, geometry isn't just an exam topic. It's literally the invisible blueprint of reality. So next time you step outside, I challenge you. What hidden angles are keeping your world standing straight? Keep decoding, and I'll see you in the next explainer.